Welcome to our tutorial on determining whether a system of linear equations is consistent. Today, we'll solve this problem step by step using an augmented matrix approach. First, let's understand what it means for a system to be consistent. A system is consistent if it has at least one solution. If there's no possible solution, we call it inconsistent. To determine which one our system is, we'll set up the augmented matrix representing our system of equations. Notice that in the first equation, there's no x1 term, so we'll write it with a zero coefficient. Now, we'll perform row operations to simplify this matrix. Step 1. We notice that the first entry in row 1 is 0, which isn't ideal for our first pivot. Let's swap rows 1 and 2 to get a non-zero pivot in the first column. Step 2. Now we want to make the leading entry of the first row equal to 1. We'll multiply the first row by 1/2. Step 3. Let's eliminate the 4 below the pivot in column 1. We'll subtract 4 times row 1 from row 3. Step 4. Let's clean up column 2. First, we'll eliminate the negative 3 halves above the second column pivot. We add 3 halves times row 2 to row 1. Next, we need to eliminate the negative 2 in the third row of column 2. We add 2 times row 2 to row 3. Step 5. Now let's inspect our final matrix. Look carefully at the last row. It says 0x1 plus 0x2 plus 0x3 equals 15. This is equivalent to 0 equals 15, which is a contradiction. This row represents an impossible equation. When we get a row where all the coefficients are 0, but the right side is non-zero, it means we have a contradiction. This tells us that the system is inconsistent and has no solution. Think about it. No values of x1, x2, and x3 can make 0 equal 15. Geometrically, this means the three planes represented by our original equations don't intersect at any point in three-dimensional space. In conclusion, to determine if a system is consistent, we use Gaussian elimination to row-reduce the augmented matrix. If we end up with a row where all coefficients are 0 but the constant term is non-zero, the system is inconsistent and has no solution. Otherwise, the system is consistent and has either one unique solution or infinitely many solutions.